Okay, so we've got this motion of Josephine the bunny rabbit. And Josephine the bunny rabbit is a very physics-driven rabbit. And what we're going to do is figure out what the displacement of Josephine the bunny rabbit is, the total displacement for her entire journey. Unfortunately, a portion of the journey she had irregular acceleration, which means that there's this curve for this portion of the graph. And that being the case, I'm going to suggest that we use one of our new skills, which is to take this graph, this curved portion, and cut it up into slices. I'm not going to do this for you, but you're going to cut it up into equal slices, and you are going to go back through and put horizontal caps on each of those slices in order to approximate the area under that curve. The other thing that you're going to do is recognize that there are multiple legs of Josephine's journey. And so there's this, what I'm going to call displacement A, and there's a list of the displacements down below here, A, B, C, D. We've got displacement B, and displacement C is a little bit strange as well, because Josephine's already up to 20 meters per second. Boy, that's a fast rabbit. But then she speeds up even more. And so we actually have the area under this portion, but it includes a triangle and it includes a rectangle. And the total displacement for that duration of time, between 20 and 30 seconds, would be the sum of that. So the area under the graphed data, the area between the graphed data and the time axis. And so maybe we have two simple ones. Remember, the area of a triangle is base times height divided by 2. Then we have one that's a little bit more complicated, and then we have an even more complicated one that's going to take a little bit of thinking to get the approximate displacement. Now, because of that, we're going to have some answers here. And we're all probably going to agree on the first three. But because the fourth leg of this journey, displacement D, is an approximation, we're all going to be kind of in the same neighborhood. And we have to be okay with approximations being in the same neighborhood. Okay? And so that's what we want to make sure that we have is an approximate agreed upon value. Okay? So that's going to be your job. You got to find first the displacements for the individual portions, and then part B says to sum them all up. Find Josephine's total displacement. Okay? Now, if I wanted to be really good about this, and if I wanted to make sure that I have the feedback, because people always want to know, did I get the right answer? I'm going to say, in the end, if you've done everything correctly, I want to put it out there that you should have an answer of about 770 meters for the displacement. And I say about because there's an approximation method going on here, okay? So I'm going to leave it at that. You got your instructions. And I was mentioning earlier about how this finding the area under curves is something that's really been kicking around for some time. This particular version, this Japanese school of thought, is between the mid-1600s to the mid-1700s, and it predates Newton's approach, and also pretty good.